You can see my screen. Hello.
No, sir.
No, no, sir.
Oh, I forgot to share it. Now,
Yes, sir.
so let's start with equivalence relation on a set. Okay. Hmm. So you know what is an equivalence relation? A relation which is Tamanna what? Symmetry.
Reflexive symmetric transitive.
Yes. Transitive. Okay. So let be an equivalence relation on S. Okay. Take X belongs to S. Right? You know what class X denotes? Or maybe this thing. What this denotes? This is defined to be set of all y in A such that X is related to y. Right? So the class
Yes,
of
sir.
X contains all those y which are related to y. Right? So observation 1. X belongs to class X, right? Since X is related to itself because this is an equivalence relation, right? Okay. Observation 2. Observation 2. For any x y belongs to S, either class X intersection class Y is phi or class X equal to class Y. Now you see, so if class X intersection class Y is not phi, if it is not phi, there exists Z belongs to class X intersection class Y, right?
Yes, sir.
So this implies X is related to Z and also Y is related to Z, right? But you see, what this says? This says that, sorry, yeah. So what does this say? This say that Z is related to Y, right? If Y is related to Z, S is related to Y, right? Because this is a Symmetric relation, right?
Yes.
So you see, so now you have x related to z related to y, which means x related to y, right? Because the relation is transitive.
Yeah.
So if x is related to y, you get y belongs to class x, right? And similarly, you will get similarly you will get, we can show that x belongs to class y. Clear? Observation. Okay, not exactly observation. Let's make a note within this observation. Okay, let's make a note within this observation. If x belongs to class y, then class x is a subset of class y. So because take any w belongs to class x. Okay, now x is related to w, right? But since x is in class y, you also have y related to x, right? Because of the transitivity, you have y related to w, that is w belongs to x. Okay,
Yes.
so now what you can say from here and here, I mean, if 1 and 2, combining 1 and 2 and this note, what you can say? Combining 1, 2 and this note, you can say that class x equal to class y, right?
Yes.
Because this will show
Yes,
class
sir.
y is subset of class x and this will show class x is subset of class y, so they are equal. So you see observation 2 is, I mean, proven. Now observation 3, we say P subset of SI such that SI subset of S, I mean not all, huh? Not all. So we say that, I mean, what I'm trying to say is that we are calling a set of subsets of S to be a partition we may not need all the subsets. Hmm. So A set, not maybe, we should say a collection of subsets, a collection of subsets of S, P in this case, is called a partition of S if one, these two must be satisfied. Okay, these two must be satisfied. One, S is disjoint union SI. Okay, that is, disjoint union means, okay, so maybe I should write this, AC is union SI. So you understand? AC is union SI. This set, this union should exhaust SI.
Yes.
And 2 SI intersection SJ is phi if I not equal to J. Understood? Together we can write it like AC is disjoint union SI. Okay, this is the sign of disjoint union.
Yes, sir.
From observation 1 and 2, you can see that we can say that if an equivalence relation is defined on S, then S is disjoint union class X, right?
Yes.
X belongs to, what I should say is that X belongs to, these are disjoint, huh? You are considering only disjoint subsets. You are not considering, maybe I should write X belongs to different classes. Okay. Right, Tamanna? We can say that from observation 1 and 2.
Yes, sir.
So now, let G be a group, and H subgroup of G. Okay. We have taken G to be a group and H to be a subgroup of G. Clear? We define XH to be the set of X into H, where H belongs to H. This is clear? This is a subset of G, right?
Yes, sir.
This is called the coset of X with respect to H in G. Okay, so this is a set test. We are taking H and you are left multiplying that with X. That's it. Right multiplying that with X. Okay. Take this set. We should write it as T. XH. X belongs to set of all distinct, or maybe set of all cosets. Okay. Set of all cosets of H in G. Okay. This is denoted by G mod H. Okay. When we say G mod H, we denote the set XH, the set of all cosets of H in G. Okay. Define on G by X is related to Y if X Y inverse belongs to H. Is this an equivalence relation? Is this an equivalence relation?
Yeah.
Give me 1 minute. Just 1 minute. Hello. So is this an equivalence relation?
Yes, sir.
Hmm. Because you see, so so one x is related to, I mean I should write x inverse is equal to e, that is in h. This implies x is related to x y inverse. I mean if you have x related to y inverse, I mean x related to y in implies x y inverse is equal to h belongs to h. I mean some element is in it, right? So if you just inverse it, you get yx inverse is equal to h inverse. That is also in h. Thus you get y is related to x. And also if you have x related to y, y related to z, then you basically have x y inverse is equal to h belongs to h, and y z inverse equals to some h prime belongs to h. And if and then you multiply this, you get h into h prime. This is also in h, right? Because h is a subgroup. This is what? Sorry. Maybe I should write what y z inverse. Y z inverse, right? So this is x z inverse, which is in h. So x to z. Thus, this is an equivalence relation. Correct?
Yes.
Can you check this? Can you check that class x with respect to this relation is basically xh? I will give you guys 2 minutes to check this. Is it true? So you see, suppose y belongs to class x. Okay. This means what? X is sorry. X is related to y, right?
Yes.
Yes, sir.
right? True that is. Now you see this thing. You multiply this by y. What do you get? Right?
Yes, sir.
In the right process. Just a minute. Then x y inverse just a minute. So x each, right? So I have to write y I will have to write y equals to x h. So for that I will have to write y x inverse. No, x inverse y. I have to write x inverse y. X inverse y equals to h. That means I need this. Okay, I need y to be xh for some h. For that I need x inverse y to be look like this. Just a moment. Give me a minute. Hmm. So as you can see, so I need this. See, I never prepare before a class, okay? I take it spontaneous. So there will be things where I am stuck, we are stuck, and we will figure it out together. So I need this. It means that if I if I take the inverse, what do I get? So it means that x inverse is related to y inverse, right? Right, right, Shojato? Because this is nothing but x
Yes, sir.
inverse y inverse and inverse, right?
The inverse, yeah.
That's what we need. Okay.
Yes.
Okay, so we can do one thing, I guess. So we have this, I think, x related to y, okay, and we also have x inverse related to x, right, which is related to y, which is related to y inverse, that is x
Yes.
inverse is related to y inverse, that is x inverse y inverse z inverse belongs to h, right, that is x inverse y belongs to h. So you have x inverse times y equals to h for some h, right?
Yes, sir.
Y equals to xh. Clear? And for the opposite, so
Yeah.
you have that class x is a subset of xh. That's what we have arrived. I mean, class x is inside xh. But what about the other? So if y belongs to xh, then there exists h belongs to capital H, such that y equals to x times h, right? Which means x inverse y is is in is equal to h belongs to capital H, right?
Yes, sir.
Then
Yes.
just as before, if x inverse y is there is equal to h, then we have x inverse related to y inverse, right? But we know that x is related to x inverse, that is related to y inverse in this case, and which is related to y. Thus, we guess x is related to y. Okay, that is y belongs to class x. Clear? Thus, we have xh is a subset of class x. So now we have the equality, right? That xh is indeed class x. So from the previous observations, what can we say? G is disjoint union of xh, right? Right? Distinct posets,
Yes, sir.
right,
Yeah.
Tamanna?
Yeah.
Okay. This will be our observation 4, I think, right?
Yes, sir. 4.
Observation 4. XH is bijective. XH is bijective to YH. Okay. That is, there is a bijection if from XH, maybe we should write this. Okay. Can you tell me the map? So if from XH to YH, what will it be? So we are taking XH, okay? You are sending it to what? YH. That's it. That's it. Nothing else.
Yes.
So let's check the well-defined nest first. ठीक है? If x dot h is x prime dot h, this means x is equal to x prime, because you can multiply both the sides by h inverse. Thus you get thus you get, no, actually the well-definedness you need not to check, because you are picking up an element, you are sending it to there. I mean, there are not, I mean, many representations. So the well-definedness need not be checked actually. I mean, what I wrote was enough actually. X equals to x prime. So that means fx is, I mean, fx will be equal to fx prime, because I mean,
Sir, here X is like,
yes, go ahead.
सर हमें एज मतलब एज कंसिडर मतलब एज का लेना चाहिए ना कि मतलब एक्स आप एक्स एक्स डैश लिख रहे हो पर एक्स तो
Mm-hmm. Sorry,
कांस्टेंट
sorry,
रहना
sorry,
चाहिए
sorry,
ना.
sorry, 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 sorry. Right? That means YH is equal to YH. Good, Tamanna. Clear?
Yes sir.
So this is well defined. Okay? Well defined. Now what about the injectivity? So if xh is equal to fxh prime, then you have yh is equal to yh prime, which is h equal to h prime, then xh is equal to xh prime. Okay? So this is injective. What about the onto? So you take yh belongs to y capital H. And what is the pre-image? Just xh, right?
XH.
Yeah. So f is a bijection, clear? Right? F is a
Yes.
bijection,
Yes
right?
sir.
Note. Take y equals to e. Then what do you get? H is bijective to xh, right? Because EH is what? H, right? So every xh is bijective to H. Clear?
Yes.
Yeah.
Let G be finite. That is, let mod G equals to n. Okay. Then of course mod H is also finite, right?
Yeah.
And from the previous note we have the cardinalities are same, right? So we had written G is equal to xh, right? Right? And we wrote like the set of all cosets, right?
Yes.
But you know what? We have shown that two cosets are either disjoint or equal. So we can write this as xih for I running from 1 to n, where these are all distinct cosets, right? There is no point in taking the same element twice. So we can write G mod H. Actually, if G mod H is a set, you cannot write, I mean the same element twice. So set theoretically. So xih we can regard it as the set of all distinct cosets of H in G. Okay. So here also we are taking the disjoint union. Thus this is nothing but xih I running from 1 to n. Correct. So what is mod H? mod of this thing, right? Now since this is the disjoint union, this will be the summation, right? Correct? Oh, mod G was taken to be n, right? Aha. These two n are not same. Let's write it as n. Correct? Thus you have n mod H. Thus you see mod H is m by n. Sorry, what I wanted to write is that m by mod H, I mean this is mod G by mod H, that is m by mod H. Okay, so you see we have order of a subgroup divides the order of the group. The fact is established, right?
Yes, sir.
Yes,
Clear?
sir.
This is called Lagrange's theorem. So you see, we have used only the definition of a group and a subgroup. Everything else is a class 12 level knowledge, right?
Yes, sir.
But from the next class, we will be thoroughly following Hungerford. Okay? Because I think if we are going through, at least in the early stages, you are only BSc, in BSc. So if we are going with a particular textbook, it will be easier for you to go through it. I mean, so you can revise it from the textbook itself. Okay, so we
Okay, sir.
will be going through groups. Okay, so Hungerford will be our textbook. We will start with monoid. This first section is not something I like very much, so we can start directly with the second section. Homomorphism and subgroups. Subgroups you know, so we will start with homomorphisms. Okay.
Yes, sir.
Okay, sir.
Okay. So Shoyata and Tamanna, I think we conclude here. See these notes. Okay.